Bonjour and good afternoon. Welcome to WASA Distance Education Center and PLAR Science. We're into week 6 and we only have one class this week, and that's only for today for PLAR Science. As you know, on Monday was a holiday, so we didn't have a class then. Just a reminder for tomorrow, Thursday, I will not be in the office. There are several of us visiting Mishkegugabang tomorrow, May 23rd. So if there are any students from Mish listening, please come to the Learning Center. We will have some pizza, or we will be bringing pizza and cookies and some fruit. So come to the Learning Center tomorrow. I think we'll be there by noon. So yeah, come and visit us. There will be myself and Bonnie, Kobe, Linda, Daryl, and Candace. I think I've got everyone. There's 6 of us. If you want to apply for a course, so either the summer term, which starts term 3, June 24th to August 23rd, that summer term application deadline is June 28th. So we have courses for English, math, science, history, and co-op. You can sign up using our WASA application online, or if you want a hard copy, you can call the office and we can send that to you. Also continuing the term 2B draw, so WASA will have 2 student draws, one for students who earns a credit and then one for students who submit work. So make sure that you're submitting your work to your teacher to be entered into the draw. And a bonus is that students working on more than one course will also have their names entered for each subject they submit work for. So get those key questions in and have your name entered for those draws. As always, make sure that you contact your teacher if you're having any problems. On the front page or the cover page of all the courses, the office number, fax number, email, if a teacher has Facebook, all that is on the first or on the cover. And then for your options to submit your key questions, you can have your DEC fax it, you can scan it yourself, and then email to studentwork@nec.on.ca. Just make sure you CC the teacher that's marking your work. You can use your Notes app to scan email, you can send a picture through Messenger, or you can drop it off at our WASA office. So lots of ways for you to get those work in. And remember, you can submit your work as you complete them. So you don't have to complete the whole lesson when you're submitting work. As you're completing them, you can submit them. And remember to contact your teacher if you need help. So we're finishing up lesson 3, which is chemistry, this week. And then we will start working on our lesson for physics. Now physics it's a short lesson. So we might even do that in maybe a class and a half. And then we will look at the environmental science. That's also a short lesson. And then you can have time to do your culminating for your PLAR science at the end of week 9. Now students who still have the culminating for PLAR science, that's students who have completed all 5 lessons, make sure that you complete them before we're done June 13th. Okay, so that's your last day to submit it. Make sure you complete it so that you can get your equivalent credit. If you don't submit the culminating, then even if you complete all of the key questions, you will not receive your equivalent credit for PLAR science. For this afternoon, so if you're looking at your mark sheet, so students who have submitted work, whether you submitted 1 key question or if you submitted 40 key questions, you will get a mark sheet just like what I have here on the slide. It tells you the total for each lesson. So for this afternoon, we will start with key question 52, and Our last key question for PLAR science is, for chemistry is key question 63. So let's see how many we can get done for this afternoon. Now each of the key questions that you have, its description is in your lesson book. So we did as far as key question 51, so we finished that chart. We will look at physical change, chemical change, that's key questions 52 to 53. And your very last key question for lesson 3 is about hazard symbols. So remember that your support questions, that's just for practice. The answers are at the end of the lesson, so you don't need to submit that for marking. Okay, if you're following along in your book, page 33, physical changes versus chemical changes. Then we will look at change of state and chemical equations on page 34. Page 35, writing chemical equations. Page 36, the law of conservation of mass. Page 37, balancing a chemical equation. Then we'll look at safety rules for using chemicals, and then that will include lab safety, chemical hazards, and finally hazard symbols. Quick review from our last class. We looked at the language of chemistry, and we said that is the same all over the world, and that's done that way so that it avoids confusion. We also looked at some common elements on the periodic table. Remember, we are not memorizing the periodic table. Okay, that's there for you. You don't have to memorize it. We also looked at a chemical formula. We said that compounds are written in a chemical formula. So for example, the compound for baking soda, the formula is NaHCO3, and that's sodium hydrogen carbonate, but we know it as baking soda. And it tells you that that baking soda contains the elements sodium, hydrogen, carbon, and oxygen. So when you look at that formula, it says NaHCO3. So it has 1 part sodium, 1 part hydrogen, 1 part carbon, and 3 parts oxygen. You then add all the atoms together, so you have 1 plus 1 plus 3. So you have a total of 6 atoms, okay, in a molecule of baking soda. Finally, we looked on page 28 at how a mixture is different from a compound. If they do not combine chemically, that means they don't make a compound, they make a mixture. So none of the substances in the mixture has been changed chemically. Whereas the elements that make up a compound, they lose their individual chemical properties, which means that the new compound has its own chemical properties. So you have baking soda as a compound, whereas you can have a salad mixture or a bowl of salad, that's a mixture. So you can have all different parts in there. You can see the lettuce, tomatoes, peppers, onions, so whatever you put in your salad. Okay, it's not, none of the substances in the mixture has been changed chemically. Okay, they still keep their own properties. Okay, let's look at physical versus chemical changes. So remember, chemistry is the study of matter and the changes it undergoes. So that's what we're looking at here. There are different ways you can change things. For example, you take paper, for example. Okay, so that's matter. You can tear up a piece of paper into small pieces, but what you still have after you tear it up, you still have paper. But you did change the way that the paper looks. But you haven't made anything new out of it. What you have done there is you made a physical change. However, if you burned the paper, what would you have? Well, it's no longer paper. So in this case, the substance has changed. Okay, and that's a chemical change. So physical, if you just alter the way that it looks, but it's a chemical change if you create a new substance. So more examples of physical changes: crushing a can, melting an ice cube, boiling water, mixing sand with water, breaking glass, mixing green and red marbles, chopping wood, shredding paper, and dissolving sugar in water. These are all physical changes. Okay, you're just changing the way it looks. Chemical change. What happens in a chemical change is that atoms are rearranged into different molecules. Both physical and chemical properties also change. Changes are not reversible. That means you can't take it back. So for example, if you burn paper, you can't unburn it. And then energy is often produced. So fire or heat, for example, that's energy. A good example is roasting a marshmallow. Okay, because when you put the marshmallow in the fire, it creates something new. The new thing is the caramelized sugar, and that's why it's considered a chemical change. Evidence that a chemical reaction has occurred. So if you look at matter and you want to show that a chemical reaction has occurred, a new color appears, heat or light is given off, the change is difficult to reverse. Like I said, if you burn paper, that will be very hard, if not impossible, to reverse. Bubbles of gas are formed. A solid material called a precipitate forms in liquid. Other examples of chemical changes: if you strike a match, you release heat and light, and then your result, you get ash, smoke and gas. Cooking bread, you change the color, texture, odor, taste. Silver tarnishing, that's a chemical change. Food rotting or souring, that's a chemical change. A nail rusting. Okay, so if you leave out your hammer outside and now it's raining, possibly snowing, and then we get sunshine, you will see that your hammer will rust. Okay, let's take a look at the next slide here. So look at some of the pictures and try to figure out whether the picture tells you, or you can identify if it's a physical or if it's a chemical change. Okay, the first one is breaking glass. So we can put P for physical or C for chemical. So if you broke a glass, okay, that's a physical change. You're just changing the way it looks. Okay, same thing with slicing bread. You're just changing the way it looks. Roasting a marshmallow, we saw that. Okay, that's a chemical change. You're creating something new. You're making caramelized sugar. Popping popcorn, that's chemical. Okay, one thing to remember with making popcorn is you add heat to it. Bleaching or coloring your hair, okay, that's a chemical change. Burning wood, that's also chemical. You're creating ash. Okay, mowing the grass, you're just changing the way the grass, so you're cutting. So you're cutting the grass, so that's physical. Milk that's spoiling, that's chemical. Freezing a popsicle, okay, so that's also physical. And we're going to look at like freezing evaporating. Okay, those are change of state, melting. All those are physical. They're physical changes. So in your book, you can check this out yourself. We're not going to watch that. You can check out this video. It's about physical versus chemical change. That is the link. You have that link in your book. It's 5 minutes and 13 minutes. And it tells you about physical versus chemical changes. Okay, so it's only a short video, but you can watch that yourself. Okay, change of state. I was just talking about that. So melting ice is an example of a change of state. So a solid, which is ice, changes into a liquid, which is water. Okay, the reason that this is a physical change, it is because what happens here is the formula for water is H2O, which is 2 parts hydrogen, 1 part oxygen. The formula for ice is also 2 parts hydrogen, 1 part oxygen. So you have both ice and water having the same chemical formula. That means no chemical changes are taking place. So a change of state, meaning melting ice, is a physical change. Energy, however, is taken in when ice is melted. And this is the only time that energy is taken in or given off. Okay, so changes of state are the only physical changes where energy is taken in or given off. Okay, make sure that you make a note of that. Okay, next up is chemical equation. So what is it? Well, like we said, when you tear a sheet of paper into tiny pieces, you still have paper. Each piece of paper, no matter how small, okay, is still paper. The way the atoms are linked together does not change. You have no new products. That means you haven't created anything. The properties of the paper have not changed, neither has its formula. That's why we say that a change, like tearing paper, is a physical change. You only have appearance changing, but the chemical makeup is still the same. Whereas in a chemical change, this is caused by a chemical reaction. So the story of a chemical reaction is called a chemical equation. And a chemical equation will show you 2 things. The first thing it will show you is that which substance or substances we start out with. So these are called your reactants. And which substances or substance we end up with, which are called products. So think of your reactants as your ingredients. So let's say you're planning on making a cake. So your reactants are your ingredients, whether you have milk, sugar, flour, eggs. And then the substances that we end up with are called products. So that would be the cake that you made. So that is a chemical equation showing you 2 things. You start what you start out with, your reactants, and then what you end up with, which are your products. Here's an example of a chemical equation. So Fe plus S equals FeS. So this equation describes the chemical reactions that takes place when a mixture of iron, which is Fe, and sulfur, which is S, is heated. So that means heat is added to it. So Fe and S are the reactants. The product is iron sulfide, which is FeS. The arrow means produces or yields, just like what I said about when you're baking a cake. It might, or say if you're making cupcakes, it will say produces or yields say 24 cupcakes. So what's showing here is that the properties of iron sulfide are different from those of iron or sulfur. So remember, you start out with sulfur and iron, then you add heat and you get iron sulfide. Those are two different things. So remember, the arrow in the middle of a chemical equation separates reactants and products. So always on the left are your reactants, and then the right is your product. So this is how you add heat to iron and sulfur mixture. So it's put on a hot plate, heat is added, a chemical reaction or chemical change occurs, producing iron sulfide. Okay, next up is writing chemical equations. So a word equation is one way to show a chemical reaction. It's telling us what reacts and what is produced. So remember that reactants are the substances that you start with, and the products are the substances that you end up with. And this is what I mentioned earlier. So reactants, if you were making a cake, your reactants would be oil, eggs, milk, sugar, flour, heat in the oven. So you put your ingredients in the oven, and your product is cake. So one way to tell if a chemical reaction has occurred is to see if the original reactants can be recovered. That means if it can be unchanged. So if you burn a piece of paper, do you think you can unchange it? So if the answer is no, then that means that what you did is you had a chemical change. Okay, you cannot remove reactants from the product. Continuing with writing word equations. So the left side of a word equation will list the names of all the reactants, and the right side lists the names of all the products. Also, in every equation you will have an arrow which is used to take the place of the word yields or produces. So this is how we write the equation for the word equation for iron plus sulfur. Notice the arrow yields iron sulfide, and that's what it looks like. So you put the iron and the sulfur, you add heat to it, and you get iron sulfide. Okay, a chemical equation. This is a more conventional representation of a chemical reaction. It tells you the chemical formulas, the relative number, and physical states of the reactants and products. So here is an example for the chemical equation for the combustion of octane, and it tells you that 2C8H18G, that means gas, plus 25O2, again it still says G, yields 16CO2G plus H2O, it still says G. Okay, so octane is a component of gasoline, and then you have oxygen, and then it goes into the auto engine, and you get carbon dioxide and water. Okay, so that's the chemical equation for the combustion of octane. Now notice there are some big numbers in front of the elements, and then there's the subscript that we talked about, or the smaller numbers to the right of the element. So these numbers or letters are found in a chemical equation. The first one is what's referred to as coefficients. So coefficients mean They are the large numbers that are in front of the chemical formulas. So looking at the combustion of octane, the number 2 on the reactant side and 25. Okay, that's your coefficient. On the product side, you have 16 and you have 18 as your coefficient. Subscripts, the small numbers to the lower right of chemical symbols. These subscript numbers represent the number of atoms of each element in the molecule. So the subscript for the reactant side, okay, is 8 and 18. So notice it says C8, H18, and then O2. Those are the subscript. On the right-hand side, or the product side, the subscript is 2 beside O2 and 2 beside H. That means 2 parts hydrogen, and then the other one says 2 parts oxygen. Now the small letters following the chemical symbols, these subscript letters represent the physical state. So are they solid, liquid, or gas, or aqueous? In this case, the G refers to gas. So that means octane in the component of gasoline, you have 2C8H18 G, so that's the gas. And then you have 25O2, also gas. And it yields 16CO2, also a gas, plus 18H2O G. Okay, also gas. Okay, and the word or the term aqueous, that just means that the substance is dissolved in water. Okay, next up is the law of conservation of mass. If you're following along in your book, that is on page 36. So what this law states is that in any chemical reaction, there is no detectable increase or decrease in the quantity of matter. It tells you as well that matter is neither created nor destroyed. The atoms are simply rearranged. Okay, so they're rearranged into new and different groupings. So for example, burning wood, so you have wood is made up of carbon, it's made out of hydrogen, oxygen, and some mineral water. But when it burns, it combines with oxygen to produce carbon dioxide, also water vapor, and some other gases and mineral ash. Okay, one way of writing it is you got mass of wood plus mass of oxygen, which equals to mass of gases and ashes. So that's how you start. You have oxygen and carbon dioxide and water vapor. That's what you start with, and then what you end it are ashes. Another example is an iron key rusting. So an iron key reacts with oxygen to form iron, or iron oxide, which is rust. The extra mass of the rusty key is due to the added oxygen. So here's the word equation. You have the mass of key plus the mass of oxygen equals mass of a rusty key. Okay, next up is balancing a chemical equation. Now, I'm not going to get you to try and balance a chemical equation, but I will show you what it looks like. So when you have a chemical equation, it gives you the quantitative information about a chemical reaction, but only if it is balanced. And for it to be balanced, the same number of each kind of atom must be present on both sides of the chemical equation. So that means it should be, what should be on the reactant side is also on the product side. Okay, same number of each kind of atom. So remember, a chemical equation tells you what happens during a chemical reaction. A balanced chemical equation has the correct number of reactants and products to satisfy the law of conservation of mass. So there are a series of steps on page 37 to follow when balancing an equation, but remember, you won't have to do that, but you can look at it. Your main goal is identifying if the chemical equation is balanced. That means making sure that there are the same amount of reactants and products on each side of the chemical equation arrow. So remember, you have to remember your coefficients and your subscripts. So here's the example we're going to use. We have the formula for hydrogen gas is H2. The formula for chlorine gas is Cl2. So notice the little numbers, those are your subscript. So if we look at H2 plus Cl2 yields HCl, that's unbalanced because you don't have the same amount or the same number of atoms on your reactant side. Okay, it's not matching up with the product side. So what you need to do here is when you're balancing the equation, we need to look carefully at the number and type of atoms on each side of the arrow in order to make sure that they match. So on the reactant side of the equation, we have 2 atoms of hydrogen and 2 atoms of chlorine, which means that we will need the same number of atoms on the product side. So we also need 2 hydrogen and 2 chlorine atoms in total on the product side. So here's how we do that. So if we look at our unbalanced equation, we can see that if we have 2 HCl molecules on the product side, then that means we will have 2 hydrogen atoms and 2 chlorine atoms. So all we're doing here is we're adding 2 so that you have 2 hydrogen atoms and 2 chlorine atoms. So now it's balanced. You have H2 plus Cl2 yields 2 HCl. Now you have the same number of each type of atom on both sides of the arrow. And that's how you can tell if the equation is balanced. So you can see here, Al plus S is Al2S3. Okay, so that is unbalanced because you don't have the same number of atoms on both sides. So all you need to do here is you add the coefficient 2 and then the coefficient 3. Now it's balanced. So you have 2 Al plus 3S gives you Al2S3. So balancing involves making sure that the number of atoms of a particular element, in this case you have Al plus S, so that has to be the same on the left side of the reaction and the right side of the reaction. You can look at the following links that you have in your book. You can check it out: Introduction to Balancing Equations, How to Balance Chemical Equations, and Balancing Chemical Equation Simulation. You can even play the game to test your balancing skills. Okay, let's try out some key questions. Let's try key question 52. What is a physical change? And give one example. So remember, when you're doing these key questions, some of them have 2 parts. You will not receive full marks if you only do one part. So first you have to tell me what is physical change, So physical change, tell me what that is, and then give one example. So one example, and then write it down. And you should get full marks. Key question 53, same format. What is chemical change? 2 parts again. So chemical change, tell me what that is. So chemical change means, or whatever you want to write there. An example of chemical change, and then you write down what your example will be. Key question 54, what is a chemical reaction? So you just did chemical change. Now you will tell me what a chemical reaction is. And then finally, key question 55, list 3 ways that you can tell that a chemical reaction has taken place. So 3 ways. Okay, I'll give you one. One way you can tell that a chemical reaction has taken place is that a new color appears. So for example, you go to the hairdresser and you had brown hair, and then you decide, oh, I want to change, not just the physical change, but you're changing the color of your hair, and you come out blonde. So that means that a chemical reaction has taken place. However, if you just cut your hair, okay, that one is a physical change. Okay, you're just changing the way that it's shaped. Okay, in the table below, key question 56, tell me whether the example on the left-hand side is a physical change or a chemical change. So you're just writing physical, or if you want to write P, or chemical, if you want to write C. First one, you're just mixing salt and pepper. Okay, so that's physical. Evaporation of water. Remember, evaporation means it's a change of state, so that's also physical. I'm not going to do all of these. Burning magnesium. Okay, burning means heat. So chemical. And then let's try one more. Demolishing a car. So that means you're just breaking it up. So that's physical. Okay, try to do electrolysis of water, cutting a marshmallow. Notice the difference. One is cutting, the other one is toasting. Rusting of iron, melting of sugar, and baking a cake. Okay, so try the rest of those descriptions. Okay, key question 57. What does the law of conservation of mass state? Okay, this is pretty straightforward. You will look in your book for the law of conservation of mass, and you will just tell me what it states. Key question 58. Okay, so this one, we'll do this together. This one says table salt can be melted. So notice that you're adding heat. So this is a chemical equation. If an electric current passed through melted sodium chloride, which is table salt, a chemical reaction takes place. This is the chemical equation for this reaction. 2NaCl yields 2Na plus Cl2. Notice underneath I have already labeled 2NaCl is the reactant. That's what's on your left side. That's what you're starting with. and it yields or produces 2Na plus Cl2. That's your product. It says the reaction has one reactant. All you're doing here is naming the reactant. So 2NaCl is the reactant, or you can say that it's table salt or sodium chloride. That's the reactant. That's what you're starting with. So all you're doing there is naming the reactant. Now it says name the two products. So you added heat to sodium chloride. You get now two products. You get Na and Cl. So those, if you want to write down the names of these elements, Na stands for sodium, Cl stands for chlorine. Okay, this part. How many chlorine atoms are on the reactant side of the equation? So on the left-hand side, how many chlorine atoms are on that side? Remember, when you see the coefficient, that's the big number in front. So 2Na means it has 2 sodium, and then it has Cl. That number in front, okay, of NaCl means you get 2Na and you also have 2Cl. So how many chlorine atoms are on the reactant side of the equation? The answer is 2. How many chlorine atoms are on the product side of the equation? Well, it says Cl2. So that means there are also 2. Is this a balanced equation? The answer is, so if you look at it, there's 2Na and 2Cl, and it yields 2Na plus Cl2. So the equation is balanced. And the reason is yes, because you have the same number, okay, the same number of each kind of atom, okay, is present on both sides. And what we mean by both sides is you have the same number of sodium, same number of chlorine on the reactant side, and the same number of sodium and the same number of chlorine on the product side. Okay, so that's key question 58. Key question 59, this one is straightforward. You circle the coefficients. The coefficients are the big numbers, and then circle the subscripts in this formula. Remember, the subscripts are the small letters beside the element. Okay, let's look at the last section. Oh, before we look at the last section, you will notice that there's a page in your lesson 3 that I have named as terms you can use with key question 44. So basically, these are all the terms that you have for chemistry, beginning with alloy, atom, chemical change, chemical equation, chemical formula, right on down to pure substances. So you can use this page, okay, it's a help sheet, and it can help you with doing key question 44. Okay, so now the last section is safety rules for using chemicals. So when you're handling chemicals, so whether it's say bleach, for example, It's a common product that we use for cleaning. You should read the labels of the bottle before you handle them. Never handle the chemicals with your bare hands and never taste chemicals. Okay, that's the first safety rule. The second rule is that you should be able to recognize hazardous product symbols. Hazardous means something that might put you in danger. For example, see the skull and the cross bones. That means acute toxic. The next picture shows a head and the chest for health hazard, and then there's another symbol there that shows you flames that says flammable. Okay, so those are some common product symbols that may be hazardous. Another safety rule is use only small quantities of chemicals and never return excess, that means what's left over, to the original container unless instructed to do so. So let's say, for example, I go back to dyeing your hair. Okay, you have your little containers there, and it says mix A with B, and then it says whatever's left over, do not keep, or do not return what's left over. That's what they mean by never return excess chemicals. Number 4, always replace the lid on the container, as some chemicals react with air or the moisture in the air. Number 5, when checking the odor of a chemical, this is something you shouldn't do, is you never directly smell a chemical. What you do is you use your hand to waft the vapors towards you. So you don't put your nose right into the chemical, but what you do is you take your hand, you kind of fan it towards you. Okay, clean up chemical spills immediately. Use plenty of water to immediately rinse any spills on your clothing, hands or body parts, or in your eyes. And finally, do not pour unused chemicals down the sink. Okay, you should always dispose of them as instructed in the activity. So when you're handling chemicals, it's probably better if you read everything entirely. That way you don't pour it down the sink and then you read after, oh, it says do not pour down the sink. So you can see on the slide there's a picture of the wrong way to do it and the right way to smell a chemical. Okay, I guess we won't finish all of lesson 3 today. When we come back on Monday, we will look at lab safety. So for now, we did as far as key question 59. We will do 60 to 63 on Monday. Just a reminder again, I'm traveling to Mish tomorrow. So make sure if you're a Mishki-Gugamang student, remember there's a few of us traveling. It's myself, Candace, Bonnie, Daryl, Kobe, and Linda. So we will be there at the Learning Center. Our arrival time, I think, is at noon. Okay, so I will see you then if you are planning to stop by there, and I will talk to you later. Miigwech.